Yeah.
Hey everyone, welcome to the lecture. Everyone's still people turning up. I don't have to talk much today. I can hand straight over to Dr. Amy Chan. So she's like me, ex-UQ PhD student, gone out into the wild and discovered the joys of industrial mathematics. So yeah, I'd encourage you guys to ask lots of questions to find out what it's like, because it's a unique experience. So I'll pass over.
Cool. Thanks. I'll just put that here-ish. Hope for the best. Let me know. I got the chat up on Zoom if you can't hear. Alrighty, so my name's Amy. I got invited by Yoni to do a perspective seminar, and I guess so you're doing all this really cool math stats programming right now and sort of have an idea of how this happens in real life, or from my life anyway. Oh, I'm meant to be standing in the camera. I'm too short for this camera, Yoni. There we go. That'll do. Yeah, so this is, I guess, take this with a grain of salt. This is sort of, it's a perspective seminar, and a perspective is from one person, right? So what I say is not necessarily how it is for everyone. It's how it's been for me, which is very different. I can't remember how to go into presenter mode, so we're just going to scroll through this in normal mode. So the things I'm going to talk about today, sort of my career so far, where I've got to, well, we can go through that later. Polymathian, which is where I currently work. A case study, and the case study is called Statistics Isn't Just Statistics. And then a bit of sort of unsolicited advice at the end, and the asterisks, because again, this is personal advice, not like overarching, definitely correct advice. So take everything with a grain of salt, and it's really good you get 3 different perspective seminars, so you sort of get 3 different opinions, which is really nice to get. So I guess a little bit on me. I want to uncover this picture because it's a cool picture. Okay, so this is what my background is. Way back 2009, I finished my undergrad degree and then did honours. The stuff I liked then in undergrad was analysis. I did a lot of like functional analysis, real analysis, PDE, that kind of thing. And then sort of on the side through some vacation scholarships with CSIRO, I got into image analysis, because it has analysis in the name, but it's actually nothing like, theoretical analysis. It's programming, essentially, maths and programming. Although it turns out you can do image analysis in a real analysis or in a functional analysis kind of way, which is pretty cool. And then I went into honours, and I was still in theoretical stuff. So I did topology optimization. Tony Roberts, he's not here anymore, but if any of you did any subjects with him, that was his field. It's about designing microstructures that have nice properties. Again, I did it from the theoretical side rather than the practical side. And then after that, I joined the CSIRO and became a graduate fellow in image analysis, which is like a big pivot from theoretical stuff. So image analysis is a lot of programming. It's maths hand in hand with programming. And then after I finished up with CSIRO, I did a PhD, again with CSIRO, different bit of CSIRO. Funny thing, so CSIRO used to have a department called the division of CMIS, CSIRO Maths, Informatics and Statistics Division, which I was part of. And then at some point between 2013 and 2018, they decided they didn't need a division of statistics and mathematicians anymore. So they got rid of us all. And instead, everyone had to, instead of being like this central maths and stats division where you would consult out to the rest of CSIRO, you became embedded within a particular application area of CSIRO and worked there. So I landed in the biomedical area, I guess. Did my PhD with these guys doing, again, image analysis. I decided to pick up statistics. I thought statistics looked kind of useful, so maybe I should learn some. So that let's just do a PhD in statistics, even though I haven't done any in all of undergrad, and we'll see how that goes. I went pretty slowly. And then finally finished my PhD. Turns out research is not for me. It's not something I enjoy. Like R&D in a corporate kind of space, I wouldn't mind, but academia, I just can't cut it. Too hard. Went to Polymathian, and I've been there ever since. And my role has changed. This has gotten longer and longer since last year because my role keeps changing. I guess I started off as a statistician, and then I went into sort of consulting and software developing and stats together. And now I'm sort of like a manager as well as all of those other hats. Polymathian specializes in operations research. So in terms of the mathsy things that I'm doing at the moment, stats and operations research, aside from all the software and blah, blah, blah. Okay, so a bit about, this is like the Polymathian spiel. These slides look a lot nicer than those ones because this is done by our marketing guy and this is hacked together by the marketing guy. Actually, no, the marketing guy did this one, which is why this one looks nice too, but you'll see the subsequent ones. So what does Polymathian do? We deliver, this is the punchline, it means nothing really. We deliver significant value to clients with industrial mathematics. We drive better business decisions for highly complex planning and scheduling problems. So this is the kind of corporate speak that kind of tells you nothing whatsoever. Essentially what we do is software development. Industrial maths is essentially operations research. We'll go into that a little bit later. And we do operations research for clients. We deliver our solvers, our mathematical solvers as software and then sell the software to clients, because why do the maths many times when you can do the maths once and then sell it to 10 different people? All right, I've gone backwards instead of forwards. Okay, so the things that we do, all the mathsy things that we do to do our, I guess, industrial mathematics, that involves mathematical optimization, not the continuous type, the like operations research over discrete space, over decision space instead. Discrete event simulation, we've recently started to do a lot of, and data analytics is everywhere. Like you will do data analytics in order to do the other two things. Like, you know, if you're doing a discrete event simulation, you need inputs to your simulation. So you say, oh, well, what's the average transit time of this truck from here to here? You have to do data analytics to get that, unless you're so lucky and they tell you, haha, it is normally distributed with 10 minutes and blah, blah, blah standard deviation, which no one will ever tell you. They'll just give you the data and expect you to work it out. Okay, so the things that we do a lot of things. This has all been a bit wishy-washy so far, right? But essentially what we do is operations research, and it's logistics problems or scheduling problems. We've got a lot of domain areas and we sort of have one product that handles each domain area. And so behind each of these is one or more engines like optimizers that solves a particular problem that then gets sold in to many different clients. So for example, the one that, let's see, I've been in a bunch of these. I even did this. So I started off in race, moved to solo, moved to Vault, moved into simulation, moved into orb, back into simulation, back into orb. So I'm currently living at orb as the product manager there, but I've been all over. But so for an example, like let's start with race. Race is a rail planner. So you have a bunch of, your inputs are a bunch of like product that is available at various places around the country. So it could be like wheat, and you've got all these different stockpiles of wheat or warehouses of wheat. And then your demand on the other side is the demand for the wheat. I need like 100 tons of this wheat here and 50 tons of this wheat here. And then you have a bunch of constraints in the middle, like a rail network. You don't have one train in the same place at the same time. This part of the rail network has to run on a timetable, so you can only get slots every 30 minutes or something. If you're going this way, someone else can't be going this way on that part of the network. So there's all these constraints on the network in the middle. And, you know, I only have 10 trains or something, and that one's under maintenance on Tuesday. So, and I guess, given the inputs, given the outputs, the question is, how do I send my trains to get all my grain from the stockpiles to the customer in time? Because for every day that you're overdue, the customer is paying a huge amount of money to occupy space with their ship at the port. And so that's just a logistics problem, right? And so we've got this tool called Race, where every day they can import their demand and their supply and their rail constraints and their network constraints. They click a solve button and they'll get a rail plan out of it. And so we've got very similar things for maritime energy, mining, blah, blah, blah. We'll have a look at Vault later. That's somewhere I've been in recently, or last year anyway. I keep going back to this. Remember, okay. So what tools? So this is just a smash together all the previous slides. So licensed products, that's not useful. Software development, support and training, managed service, optimization, event simulation, data analytics. This is all stuff that we do in our job. But really, what tools do we use? So we can start with software development. You guys have been doing a lot of software development. Julia is an excellent language for a lot of things, really, like data analysis and stuff like that. I'm not super familiar with it because Julia was only new when I was graduating. So I sort of grew up in R at MATLAB. Python we use for our actual backend stuff. We use React and JavaScript for our front end stuff. So we sell a lot of websites. I'll show you that. So it's a web app that runs some maths in the background. So the maths is in Python and C++, but the website's in React or JavaScript. We deliver websites through AWS. So I'm sort of pivoting into a bit of IT stuff here, not really math stuff, but basically everyone who's delivering apps over the web are doing it through AWS. Docker is another tool that helps you do so. The optimization itself, it's operations research. We're generally using Gurobi or Cplex. We're generally using C++ because it's faster, but the Python interface is much easier to use. So if you're learning this kind of stuff, start on the Python interface and only move to the C++ interface if you have to. Discrete event simulation, we use SymPy. There are lots of different discrete event simulation packages out there. And then data analytics, use whatever tool suits the job. So for me, that's R and Python. For you, it might be Julia. No one really uses MATLAB because MATLAB licenses are really, really, really expensive, and R is free and Python is free. And I think Julia is free. Sometimes you have to use Excel. I spent the whole day today using Excel. That wasn't very fun, but it happens. All right, so unsolicited advice number 1, don't let lack of domain knowledge stop you from trying. So this is a huge variety of domain areas in here, but it's all maths. Right, and it's not even the same type of maths, but it's all maths. Like, did I train in statistics? No. Did I train in image analysis? Of course not. You can pick it up. So this is what I did with Cyro when I was a graduate fellow. We had this cool little helicopter here that you can see in the picture. This is an autonomous helicopter. It flies itself. That's the coolest thing ever. When you go to site and they fly it, they say if it comes down, you have to run into the van because these blades will get you. This is before quadcopters became really like robust and good. So this is a little petrol helicopter, epic. So what did we do? We attached a bunch of cameras to the bottom. So like LiDAR, which measures distance and heat, and just normal thermal, like normal visual, like RGB color cameras to the bottom. You fly it over these giant fields of wheat that you can see in the middle left. And then you take pictures looking down. So you get a whole bunch of pictures of wheat, and they look basically the same. The picture taken here looks the same as the picture taken next, and the picture taken next, and the picture taken next. And so the image analysis, the job that I was doing there was basically taking all of these pictures of fields of wheat that look the same and trying to stitch them together into a mega picture of the entire field of wheat. So you can see like this is only the top corner of the field of wheat. So you would process all the images, you know the GPS of where the helicopter is at the time, like the attitude, like the angle that it is relative to the ground. So you can sort of work out how to square up your image and stitch them all together. And then once you've stitched them all together, you do some analysis on the data. So on the bottom right here, on the left-hand side, this is actually a picture of sorghum through a heat camera. So you can tell the temperature of your sorghum. Temperature of sorghum is not generally very interesting, except that it's a really nice way to work out how much of the ground is covered by plant. So otherwise you can do it visually with these middle two images. And essentially the question is how much of the ground is covered by plant? 90% of the ground is covered by plant, or 33% of the ground is covered by plant. And this is sort of a metric for how well your plant is growing. Like this poor little guy in the bottom with 33% covering, he's not doing well, right? Because he's only a third alive, the rest of him died. Whereas the guy at the top is probably a sorghum that you want. So basically my job is to get these numbers from the images, pass them on to statisticians. I wasn't doing statistics at the time, and the statisticians would do stuff with these numbers and say, aha, this fertilizer and that variety of wheat or sorghum is the one you want. So that was my Cyro job. While I was at Cyro doing that, at the same time, someone said, oh, here's a bunch of images I've taken of, this is like the meristem of wheat, but it's like baby wheat. And there was actually not in this picture, there's a ruler in each of these pictures. And basically the job was, can you automate measuring the volume, the surface area, like telling me how big this wheat is from the picture, because I don't want to do it by hand. And so just for you to extract, it's really easy, right? Because the wheat's bright yellow and the background's black. So you extract this bright yellow object, you measure it, you have to extract the picture of the ruler out so you can measure it against the ruler, and then you have a metric for how big the wheat is. And then you give those numbers again I gave them to Ursula, who's the first author here, and she did all the work. So I was just doing the image analysis, but this is just cool stuff that you can do while you're at Cyro. This is my PhD. We are running out of time to talk about stuff. This is on brain MRIs. So So this is a brain MRI to the left. There are kind of three main tissues in your brain. You've got the dark bits in the middle, that's cerebrospinal fluid. You've got like the squiggly bits around the outside, which is your gray matter. And then you've got the stuff on the inside, which is your white matter. And what can be interesting to do with brains of people is to take measurements of them. For example, how thick is their white matter? Oh, sorry, their gray matter, or how big are their ventricles? And you can track that over time. So you get a model of how your brain changes when you age. And then you can track them across populations. So you can say people with Alzheimer's have really big ventricles, or their ventricles grow much faster than others, or their white matter, their gray matter gets really thin in this particular part of the brain. And so you can use this to try and diagnose or do research. Anyway, before you can do any of that cool stats, you have to extract the brain from that picture. So on the very right, you see like a segment, it's called a segmentation of the brain. So basically all the different bits of tissues, this is a different brain to the other two pictures, which is why they look nothing the same. And so from that, you can then, you've got like a model of the tissues in the brain, and then you can take your measurements from there. And so I guess the gist of it is that if you look at the colors in this brain, the dark stuff is dark, the white matter is like the lightest, and the gray matter is in the middle. So if you look at a histogram of the intensity, which is this picture here, you can just chop it up and you'll get a pretty decent initial segmentation of the brain, which is this one in the middle. But when you've got a noisy image, you get all these little dots in the middle, which don't make sense. So my white matter has, white matter has a lot of gray matter dots in them, which don't make any sense. So this thing here is a mixture model. I don't know if Jeff McLaughlin's still here, but he does mixture models. You can put spatial priors on a mixture model. Basically, you can say that if I'm a bit of gray matter and everyone around, well, if I'm a bit of, I look like gray matter, but everyone around me is white matter, I'm probably actually white matter. So you put a spatial prior over your mixture model and you get a better segmentation. So that's what my PhD was about. Okay, skip past that, doesn't matter. And then we've already talked about Polymathian, basically been in mining, in rail, in maritime, and energy, and blah, blah, blah. So this is a whole bunch of different domains. That's the point. So agriculture with a cool helicopter that flies itself. That was the coolest thing about the project, that helicopter that flew itself. Agriculture with little wheat in a microscope image. Brain segmentation. While I was at SARA, I also did a bit of premature baby statistical analysis just because I was a statistician and somebody asked me to. That was this paper here. There's a lot of interesting stuff you can do on premature baby brains or pictures of them. And then through Polymathian, I've done a bunch of rail stuff, marine pilot stuff, energy stuff, pathfinding stuff, materials handling stuff, life of mine stuff, real-time stuff. So life of mine stuff, this is like generating strategies for your mine, and a mine might live for 50 years. So that's a 50-year plan. And then on the other end of the scale, we're doing real-time stuff. So you can do lots of different stuff. This all sounds like I'm very impressive and know lots about lots of things. And I can talk just enough about these things that I sound like I know what I'm talking about to anyone who doesn't really know much more. And even sometimes I can sound like I know what I'm talking about to people who do know a bit more. But the key is it doesn't really matter that you don't have any of this domain knowledge. I didn't know any of this stuff before I went into it. You've taken with you like an open mind, your maths and your stats, and then you just apply it. It's just a domain area. So don't be scared if you look for a job and it's like, oh, you're going to be working in the hospital, Metro North, analyzing like patient data. And you go, oh, I don't know anything about medical data. It doesn't matter. It's just stats. You can learn the domain. You've got the skills. Okay. So that's the first thing. All right. That's, a bit out of order here. So I guess, why am I working at Polymathian? Basically, it's a small company, or it used to be a small company, and it's got a nice blend of everything. You get to do a lot in a small company, get to travel. We haven't traveled for ages, but we used to. We're actually traveling this year. We used to do a company holiday every year. So we went to ski trip in Japan. That's the bottom right. We went to Tasmania in 2020 for a hike right before lockdown started. And then a bunch of various hikes. I drag people hiking and climbing when I can. And we're going skiing again this year, finally back. All right, so when you're looking for jobs, there are a few things you've got to think about. What do you want to do? Academia, applied research, private sector, it's all really different. Sometimes it's just try, see what you like. A really good way to try is through vacation scholarships and internships. Really good way. And honours is a really good way to try academia. It's only 1 year. PhD is not a good way to try academia. I'll warn you, don't do a PhD unless you know you like research or you've got a question you want to answer going in. Don't just drift into it and go, I think I should maybe do a PhD, which is what I did. That's not the way to go. But honours is still a very good. It's only lasts 1 year. It's a great way to try out research. How much programming do you like doing? I have a very strong lean towards programming. I love programming. I'm actually working as a software developer now, more so than a statistician, but you can control that. Just know that depending on where you want to sit on that scale, like will limit or expand what you can apply for or direct what you apply for. Do you want to go into grad program or not? Grad programmers can be nice because they generally are designed to give you a tour of everything in a company. Only big companies tend to have a grad program. So pros and cons, you generally get a nice amount of mentoring in a grad program, whereas if you're not in a grad program, you're sort of just at the luck of how good your team is at training you. Big company or small company, this sort of goes with the grad program a little bit. Small company, you get to do more. That's the thing I love most about when I joined Polymathian, I was the 20th employee. We now have 50 employees. But since we only had 20 employees, I could do everything. So I got to write proposals, talk to the clients, do the data analysis, do the data mangling, do the operations research, do the programming, present it back to the clients, train the clients. That's so cool. I like that. In a big company, you generally don't get to do as much. You have a slightly better defined role. This can be a good thing depending on what you like. I'm not saying one's good and one's not. It's up to you. In a big company, sometimes I wish I had more people to learn from. Like if you've only got 20 people, that's 19 people to learn from. If I've got a company of 100 people, it's 99 other people to learn from. So it's up to you. Do you like working in a team or do you like working as an individual? I hope you like working as a team. It's a bit harder. It's harder to find places where you can work as an individual. And then company culture. Don't discount company culture. Like you're spending a third of your life at work, you may as well enjoy it. That said, you can make company culture if it doesn't exist. I would say Polymathian had excellent company culture before I existed, before I came, but Poly Climb Club, which is this middle picture, and Poly Hike Club, which are these top two pictures, that's me. Poly Board Game Club, watch this space, we're there. And then vacation scholarships and internships, we would touch on these. I really recommend them. Really short, low risk way to decide what you like. Right, case study. Got to talk faster. So the case study is statistics is not just statistics. So I guess, I know this is more maths than statistics, this course, but so, you know, you dream of being a statistician. So, well, nobody dreams of being a statistician, but you think of being a statistician and you go, right, I'm going to be doing awesome stats. I'm going to be fitting models left, right, and center. I'm going to be doing all this really crazy, complicated stuff. And it turns out that the majority of your work is not the cool stuff. Or, you know, it's not that it's not the cool stuff, but statistics isn't just the model fitting part, the flashy part, it's also all the other parts. So that's sort of the direction of this case study. Oh, you laugh, but I've had some funny requests from clients about Excel. Okay, so we're going to go into Vault. Vault is one of the products I was talking about. It's one of the products that Polymathian has. Vault does blah, 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 blah. Let's have a look. Allow. Actually, no, I had this open here. Okay. So this is Vault. So this is, when I said that what Polymathian does is software as a service. So this is a software that we deliver. And we have a bunch of, each app, essentially, we have a bunch of different apps and each one solves a different problem. So we can start with this one. So what Vault does is there are sites around the world and you imagine you are in charge of a bunch of energy generating assets and a bunch of steam generating assets. Steam gets used by a lot of factories in their manufacturing. And so you have a bunch of customers on site where your steam and your energy are, and they have from you requested certain amounts of steam and energy at times of the day. So this customer needs like 10 tons an hour of steam, of high pressure steam, and 10 megawatts of energy. That guy needs 20 and 20. And so you, in charge of your gas turbines, cogeneration plants, your boilers, your steam turbines and stuff, have to decide how to deliver that power and steam to your customers in a way that makes you the most money. Because at the end of the day, you just want the most money. So here's a scenario where we have a bunch of assets. We've got dams, we've got wind farms, we've got hydro, we've got gas turbines, we've got cogeneration plant. Cogeneration plant is something that makes both steam and power. We've got things that make steam, things that make different types of steam, Let me drag all these windows out of the way. On the right-hand side, what we have is a bunch of power demand and then customer steam demand. And so the idea is that all of these assets here are sources, and then you've got your demands there. And in which combination do you turn these things on to make the most money? And so that's the problem that Volt solves. This is a mixed integer program problem. I need to get this out of the way, this window. I don't know if you see that window, that's just blocking my view. Okay, so this particular scenario is kind of interesting. So this one has a fixed demand of 600 megawatts. So what we're looking at is power, and each of the colors here, this is over time, the x-axis over time. And so I've said, deliver me 600 megawatts all the time in the cheapest way possible. And which assets do I turn on and when? So the interesting ones are the wind farms. So the wind farms have a predetermined input profile. Turns out that wind farms make the least wind around midday and the most wind at night, which is not something that I knew. So we put as a fixed input the amount of the predicted like wind power profile. And so really it's a game of turning on the rest of your assets to fill the shortfall that the wind can't provide in the cheapest way possible. So you can see these things are all slightly different colors, but basically you've got 3 gas turbines and you're turning on gas turbine number 3 last because it's the most expensive to run. So that's kind of a cool scenario. Here's another scenario. This one, we've got 3 gas turbines. It's kind of boring. We're not making any steam. We're only making power. And here you're not restricted. You have to deliver 275 megawatts all the time, but we've also said that you can sell power back at the market price if you generate excess. So how do you make the most money? And so what this graph here shows is, so this line, the orange line, this is the price, this is the amount of money I can get for selling power back into the pool. And then all these bars are my generation profile of which assets I've turned on to produce power. And essentially, you know, when you can get a lot of money, you turn on all your stuff and sell, because that's how you get the most money. So here, where the price of power is like you can get a lot of money for selling power, you turn on your most expensive asset, gas turbine number 3, because at this point it is profitable for you to sell power, to turn on that asset, pay for all the expensive gas and sell power. So this is an example of Volt's scenario, or the consulting app, I guess. So we use these apps, we sell these apps to clients and they upload their inputs, outputs and scenarios and click solve and have a look at the answers, or we do it sometimes on their behalf. Like they say, oh, hey, me, what would it be like if I bought gas turbine number 4? Like, how much money can I get? And you would do that for them. And then the coolest thing about Volt is that it actually runs in real time as well. So this is an anonymized version of Volt running in a real site. They've run it up on a control room. And it tells them essentially with all of their assets and all their demands. So the stuff, this one doesn't show power, all the stuff down the right is different types of steam, demand for different types of steam. And it tells you, what should I do right now to get the most money? So for asset J, you're currently making 80.9 megawatts. If you could make 80.9 plus 14.5 megawatts, you would make more money. So do that. And so they actually use this dashboard in real life to dispatch their assets. The funny thing is, sharp-eyed people, this is all anonymized, but sharp-eyed people might notice that the actual, so this is what they're actually making, the actual profit margin, and this is the optimal profit margin, and it's lower than the actual profit margin. So here's lesson 0. The reason that the actuals are beating the optimal right now is that we asked them why. One of their gas tags is not working right now. So they've got a sensor that's reading in how much gas they're burning. Gas is really expensive right now for obvious reasons. That gas tag's not working. So what's happening is that this actuals number, we are reading from their systems how much gas they think they are burning. And they're burning about half, or the data says they're burning about half what they're actually using. So they're actually making lots of profit. It looks like they're making profit. So in reality, we would be beating them. Whereas Volt is constrained to use the correct amount of gas, whereas the actuals number is fed from an actual gas sensor somewhere. So when they emailed and says, oh, how come Volt's not beating the actuals right now? How come we're doing so much? We're making $5,000 an hour more than Volt is, and it's because their data was wrong. It's because one of their gas tags is broken. So this is lesson 0. If you put rubbish into an optimization, you will get rubbish out. So make sure your data is right. The other thing that with this client, the thing that they used to do all the time would be fuss about, like, They're like, we ran the Volt model through our financial model and we see the number in your financial model and you've got 12,457, but we think you should have 12,458. What is this discrepancy? And so they would fiddle over tiny little discrepancies like that. And then you just have to say something like, oh, that gas tag of yours, is that actually on right now or is it reading rubbish right now? So basically keep an idea of the level of detail, I guess. There's no point fiddling over or fussing over a dollar difference in outcome when your inputs are rubbish. So make sure that your outputs only need to be good to the same resolution that your inputs are good. So if your inputs are out by 10%, then your outputs can be out by 10%. Don't fuss over 5%. Anyway, so this is pretty cool. So that's Volt. Let's go back. Blah, blah, blah. So what is it maths wise? Generally, it's a mixed integer program. You set up this network that you've seen, those power networks. You feed in as a source your demand on one side, you take out on the other side so you feed in your source, which is what your assets can produce. You take out your demand and you do a network flow in the middle. And then on every arc, you put a cost. So to turn on your gas turbine, it's going to cost a certain amount of gas to run it. To make a certain amount of power, gas costs this much per BTU right now. And so you build up a financial model of how much you're paying, and then you feed that all to something like Garobi and tell it to make you the most money. And that's what it does. So if you do the operations research course, you'll do problems like this. Okay, so the Volt is powered by 3 main inputs. There's the network model. So it's all data driven. So there's this, where did my, I don't know where my, okay, so there's this network model. So that's this network that we're looking at. So this is all data driven. There's a table somewhere that's nodes and a table somewhere that's arcs. And you just define how your network is connected. The other thing that Volt has is a financial model. So if you're running your asset, you need to know how much money you make by selling your contracted demand, and you need to know how much money it costs you to turn on your assets. And then the key, or the one thing that we are going to look at, is asset models. So the asset model is essentially, I've got this gas turbine, I need 100 megawatts. How much does it cost to make 100 megawatts out of this gas turbine? How much fuel do I need to feed into my turbine to make 100 megawatts of power? Don't know. So that's what we're looking at today. So the case study is basically, for one of our clients, I had to develop an asset model for their cogeneration plant. Cogeneration plant makes power and steam. And so you ask the client, like, how much fuel would I need to make 10 megawatts of power and 10 tons an hour of steam? And you'd think they'd know that, right? Because they've been operating this site for 20 years. And they don't. Imagine that. You buy a cogen plant and you don't know what it's going to cost you because you don't know how much fuel you need to feed into it. Anyway, I suspect that they do know, but the knowledge has been lost over time. It's nuts. Anyway, so what they do is, you know what we'll do? We'll give you a dump of all of our historical data forever and ever, and you can work out the asset model, because without the asset model, you can't run Volt, because you don't know how much it costs to make power or to make steam. So that's the case study. All right, so step 1, this is like a standard stats assignment, right? So you get data and then you do some data analysis. So you say, send me all of these things: gas in, power out, steam out, steam out. There are lots of different types of steam: high pressure, medium pressure, low pressure, and anything else that you think is relevant, like, you know, does it operate better on a hot day versus a cold day or something like that? And then they'd send you this. They're like, here you go, Amy. Here is a spreadsheet of data forever and ever. That's it. That's what we got. And so you go, what are these things? Like SKPV, blah, 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 SKPV, blah, 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 SW, I don't know how many columns of data that is. And they're like, great, make a cogen model. Where's the cogen model? And I go, I don't even know what any of these things are. So this is not step 1. Step 1, get the data. That's the hard thing to do. So you can't even do any data analysis till you get the data. And you're lucky because in your assignments, you get data of varying goodness and you have to then mangle it. But you actually do get data. Often you don't. Often it takes weeks to get this stuff. Okay, so getting data takes a lot of time and it takes a lot of communication. So I'm a statistician. I know nothing about a cogeneration plant except that it takes in gas and it produces power and steam. So I tell the engineer, I say, I just want, tell me which column of this is gas and which column of it is steam and which is power. And then I can do my regression, right? And they're like, oh, which ones do you want? This is bottom left. This is a diagram of how a cogeneration plant works. They're like, oh, you can put gas into the fuel, into the boiler, and that makes a bit of steam. And then you can refeed some of that, makes hot steam, and you can refeed some of that steam out and put it back in and heat it up again, and it'll be even hotter. And then, or instead of feeding it back in, you can actually put some out the side as medium steam instead of high pressure steam. Oh, and actually what you can do is feed, when you burn the gas, you can actually burn it again and get an extra boost out of it. So which gas tags and which steam tags were you after? Like there's lots in here. It's not as simple as there are some in and some out. And so it took many, many iterations of like, I'm a statistician, I don't understand this, to sort of impress that we wanted to treat this plant as a black box. At some point, stuff goes in and stuff goes out. I don't care how things are circulating within. So we're going to start with that level of detail. Here's a black box. It could be that the stat says that you need to know about the internals, but for now, let's start with the black box. So it takes a long time to try and get the data, to articulate what data you want and talk to someone. The problem is that I don't know enough and they know too much, right? So I'm talking about, oh, gas in, and they're like, oh my God, there's 100 gas tags, which one does she mean? Okay, so lesson 2 is data is never how you like it. You're gonna have to do heaps and heaps of data mangling. So eventually we got a list, like a legend for how this data looks. And so this is the top left here. And so this top tag says flow for intermediate pressure steam, and the bottom one says HP steam flow. Great, so the bottom one is HP steam, the middle one is IP steam. That's 2 of the columns I need. And then they go, oh, actually the HP steam is this one, the one that says IP steam. We just got the label wrong. The second one is actually not HP steam, that's actually like water. Great. So that's the second problem. It's never how you like it. You never get the right labels in your data. Some other examples we got. So on the top right-hand side is information that you'll often get from a client. It's in wide format. So this is like a calendar. This is when you're communicating with a client, displaying data, time series data to a client and getting it from them. The calendar view is often the most intuitive view, and it's the easiest for you both to look at. So calendar view, I'm not saying it's bad, it's excellent for showing data, for visualizing data. Calendar view is really hard to analyze data on, right? I don't know if you've done reshaping in Julia, but you start with this wide format, but what you want is the long format where you've got a column called date time and a column called value, instead of a calendar where every column is a date and then your rows are the values. So learn how to reshape your data. You're going to do that all the time. And you're always going to reshape it to long to do your analysis and then reshape it to wide to do your visualization if you're going to show it to a client, because it just makes more sense that way. You have to work out bad data, bottom left here. So they didn't tell us, but it turns out there's like in the data, this is a time series data of fuel over time. For a while, all the green dots are when the asset was out. There was just an asset outage. The client's not necessarily going to tell you that. They're just going to give you all this data. And then you look at this data, you do your regression, you're like, hang on, I shouldn't even have done the regression yet. I should have looked for bad data first. And so you identify this bad data and then you message them and you're like, what's all this green data? They say, oh, the asset was out that day, it had an outage. You can have sensor outages too, where the tag is just not reading the right value. You've got this fuel sensor and it's reading 0000. It's not because they were using 0, it's because the sensor just was out at the time. This is my personal favorite. Actually, these two are my personal favorite. In the middle here is a tag that was reading 0. They assured me that there was no P gas going in at the time, but you pull the data out, so you've got 600 kilograms an hour. 600 kilograms an hour is nowhere near 0 on the scale of these things. Anyway, they're like, oh, sorry, the sensor was actually, for the last 5 years, the sensor has actually been miscalibrated and we just don't use it, so we didn't notice. Great. And then this is the other one to the bottom right. This is that there are 2 tags that these guys have for fuel. One's a high range and one's a low range. So one reads when the fuel, basically one of them caps out after a while. Turns out the high range one is broken, so the low range one is working fine. That's that pink one, and it's kind of matching. This is the color is fuel and the line is steam. And for this asset, we're so lucky that fuel and steam kind of roughly correspond to each other. So they should line up in silhouette. Turns out whenever the fuel tag goes above a certain value, it just dies, caps out at 2000. That's it. So you're trying to do your regression and you're getting all this garbage. So prepare to do a lot of data mangling and prepare to do a lot of exploratory data analysis, because it's never going to be nice. It will never be nice. You have to go back and forth a lot. And a lot of this is like, you don't work this out. Like I look at these tags and I can't see necessarily what's going on. Often you will send the client stuff saying like, what's going on here? What's going on there? And they say, oh yeah, that's the day the gas turbine tripped. Yeah, exclude that. So it's not necessarily that you should know it, but you should be able to explore your data, identify things that don't look right, and then go back to the client and ask them again. And it's just an iterative process. Graphs are really helpful here. Aside, so if you're writing code, this is ggplot. I think Julia will probably, everyone's got a clone of ggplot. ggplot is the best plotting library there is. It lives in R, it came from R. If you're ever writing code to make plots, save that code because you might need to make it again sometime. For example, when you're writing a talk and you lost the original plot, you can just run your script and it will run again. It will generate again. So save any code that you write. Even if you're doing Excel charts, that's fine. Save that Excel sheet. Like don't just make your chart and then delete whatever you used to make the chart, because you might want to come back to it again. You might get updated data and just want to draw the same chart. So you just put your new data in, use the same chart code. All right, so ages and ages and ages later, you get data like this and you do a regression. Woohoo! This is your asset model. So this is the asset model that on the y-axis is fuel and on the x-axis is some combination of power and different types of steam, essentially. So it's a multilinear regression. It's got a breakpoint in it. It's basically a piecewise linear regression. So it turns out you can operate a cogeneration plant in like cheap mode, which is pink, and expensive mode, which is blue. And you switch to expensive mode when you need extra power. Sometimes it can be worth it. If power is going for a lot of money right now and gas is cheap, then it can be worth using expensive mode, but it's not very efficient. So you get like this funny changing gradient in your line. So at the end of the day, it's a regression, and that's kind of depressing because you're like, oh, I'm this excellent statistician and I've done all this work and it's a linear regression. That's a bit sad, but that's the way it is. So, and again, it varies by context. This is like consulting stats, which is different to like research stats. It's a power plant. Like it makes sense that fuel and steam, or like inputs and outputs, would be sort of linearly related. The main thing here is don't let perfect get in the way of good. So you can keep improving and improving and improving and improving this model. Like, well, we looked at the end of the day, we went with fuel, power, HP steam, MP steam, and LP steam. We didn't look at like, well, we did look at, but we excluded stuff like humidity, temperature, I don't know, supplementary gas, water spray, pressure. I don't know. There's many other things that you could put in to technically make your model a little bit more accurate, but you don't just, it's not needed at this level of detail. So don't let perfect get in the way of good, right? This is good enough. And this is actually another client who was complaining about, they're like, oh, look at the spread of these dots around your line. Like there's so much variability. Like we predicted you've predicted that it will cost this much fuel, but it actually cost that much fuel. Like looking at the variance there. And what you do is you sort of go back and say, well, whoops, not that far back. And you say, well, this is what I had to deal with. Like if your fuel tag is being truncated after 2000, I cannot hope to get any results more accurate than this. You can only be as accurate as your input, and the inputs were not accurate. So again, don't let perfect get in the way of good. You can watch your mean square error over and over and over again, but at the end of the day, your data might be rubbish to begin with. Okay, and then I guess the other thing is when you're communicating your results, more important than the stats itself is how you communicate them, and at the right level of detail. So p-values, confidence intervals, assumptions, you have to do them. You're a statistician, but I'm not telling the client. Yes, and we, in assignment, you do assignment. I did this regression. We have validated that the data is like the distribution of the data around the mean is normally distributed, or the residuals look normally distributed, and the data is independent. And I can't remember this, that, the other assumption. You don't put that in a report that you're giving to a client generally. Like the client just wants to know, I gave my data to some statistician, someone smart who sort of said they knew what they were doing, and they've assured me that this model is the correct model, or is an adequate model. So make sure you have the right level of detail. And it can be kind of heartbreaking because you want to go, oh, we use this cool piecewise linear regression, blah, 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 blah. And they're like, oh, you fit a line to my data. Like they don't need to know. It can be a bit sad, but it can often be a more effective way to communicate. So you have to try and reduce the language barrier when you're communicating your results to others. You're a statistician or a mathematician, your technical literacy is very high. You may be talking to someone who is an engineer of a power plant, and their technical literacy may not be the same as yours, or numeric literacy. So I can say, so initially this slide, we said, oh, we did a linear regression, piecewise linear regression. But that turned out to be really confusing. Every time we said we did a linear regression, the engineers would say, hang on, fuel efficiency is not linear. Linear regression's wrong, linear regression's wrong. Turns out we're doing a y equals mx plus c kind of job, but the KPI that they're used to is y on x without the c, which is non-linear, right? So I say linear regression, they go, oh, not linear, not linear. And it takes a while to convince them that the regression is linear, but this metric, the KPI they're interested in, y on x, is not linear, like it's not constant. So we actually changed the words on this slide. Instead of saying we did a linear regression, we said we just did a best fit. We fit the asset model, we fit to actuals. So yes, you kind of hide all that detail, but at the end of the day, it reduces the language barrier. There's no point like smashing them over the head saying, yes, it is a linear regression. Ha, look, y equals mx plus c, you've forgotten the c in this equation, and proving it to them, that's not the point. The point is just reduce the language barrier where you can. We have some weird combined our x. So this is like, there are the x variables here. There's 4 of them, power and 3 types of steam. You can't visualize that, right? Because it's a funny cube, hyperdimensional cube. So instead what we did is we condensed our outputs onto one output. We projected our outputs onto one. I know it's only one slice of the hypercube, but you can then show them a 2-dimensional chart. This word, output, it's a linear combination of power and steam. We used to call it load. Turns out load is a special word for plant engineers. It means something very specific. And so we kept saying load, and they kept saying that's not the load. And so you just change the word to output. And it's like, this is straightforward stuff. It's not unreasonable. As you work with your clients and become aware of the language that they use, if there is an opportunity for you to change your language to match theirs, it can help a lot with how well they understand what you're saying and how they receive what you're saying. Because you're already asking them to understand some statistics, that is, they're not used to it. So the least you can do is make it easier for them to understand by taking any easy wins you've got on terminology. And you generally learn this terminology just through talking to your clients. You just notice all the time, you know, every time I say load and they say, that's not actually load, like, what do you mean by load? Then I realize that load is a special word for them. Or every time I say linear regression and they say it's not linear, and I say, oh, what do you mean? What is not linear? And then realize what the issue is. You can then just stop saying linear. And, you know, this is not a confidence interval. 95% of the data points are between minus 1.6% and plus 1.8% of the actual data. It's not a confidence interval, but it's something that's really easy to understand. I don't want to explain a confidence interval to a non-statistician. So it's something that's really easy to understand. And then when they say, oh, we're in plus or minus 2%, that's okay. And then when they ask, why aren't we within plus or minus 1%? I say, well, is your input data within plus or minus 1% of reality? They say, oh, no, we've only got 5% accuracy on the input data, on the tags. So like, it's a really nice way to communicate. So you can say, well, you've got 5% accuracy on the input. We can at most hope for 5% accuracy on the output. Done. All right. So after all of that, lessons learned, don't let perfect get in the way of good. You can always improve your model. It can always be better. You can always do more, but sometimes it's good enough and you need to stop. This is one of the biggest things that I had to learn coming out of academia, because, you know, when you're doing a PhD or honors or uni, you get it perfect, right? You always go as far as you can. It turns out you don't need to in real life. It's kind of lazy. It's nice. Version control, you have to learn version control. I'm going to hammer you over the head with this later. Visualization is very, very, very important. Visualization is the main way you talk to clients rather than through words. And communication is really important. And overall, statistics isn't just statistics. So when I say, like, I could almost say statistics, like, you don't get to do much statistics in that you don't get to do much model fitting in statistics, but really it's all statistics. It's just that you need to broaden your definition of statistics. Statistics is not just the model fitting. It's the getting the data, the talking to the client, the data mangling, the data visualization, the communication after. That's all part of statistics. So you can't just go, you do a stats course and you do lots of like problems, like you do lots of, you get lots of exercises to go through, and a lot of them don't include the befores and the afters, just because that's hard to teach or hard to manage in a course at uni. But be aware that it's there. Be willing to learn it. All right, tips, asterisk. So asterisk because caveats. I'm a sort of a stats maths software engineer or software developer. I lean really, really heavy towards software development right now. Polymathian, my job, has shifted much more towards software development. We used to be very mathsy, but now we've sort of done all of our core maths and we just keep selling the same maths over and over again because we're lazy. And so now I do heaps and heaps of software development. So these are tips a little bit more as someone who's come from maths who is now into software development. So they're not necessarily going to apply if that's not your particular interest. All right, so first, numeric literacy and programming give you lots and lots of options. So all of your jobs, it's the pair together. It's like I have an analytical mind, I can problem solve, I can analyze data, and I can program the two together. The jobs they never say mathematician, they never say statistician, or sometimes they say statistician. The words you can look for stuff like analyst, data analyst, modeler, data scientist is a huge buzzword. A data scientist is kind of like a statistician. They're kind of all the same, right? You just have to be a little open when you're reading the description because it's not going to say maths or stats necessarily. Lots of really big companies have in-house statistics divisions, which is really cool, something I didn't know. All the big mining companies have in-house data science divisions, and they've got people with PhDs and they're doing crazy stats. They don't often advertise, it won't necessarily be advertised in a graduate program, but you should be able to apply to it anyway. They will have one. Maths and programming together, the main thing this offers you is flexibility. So you can do some maths, you can do some stats, you can go into software programming, into software a little bit later if you like it, you can go back. Like I feel that I can move sideways as much as I want right now. So it's not necessarily the specific maths. I didn't learn any stats in my undergrad. I haven't done any epsilon delta proofs since I've left uni, but it's the skills that you learn. It's like being able to do, like, I haven't done any epsilon delta proofs since I left uni, but I have used the thinking that you learn when you write the epsilon delta proofs, like the logic, thinking logically, that's what you use more so than the proof. So they make you do the proof because, that's how you teach it. That's how you teach the logic. And you learn that in programming too. So basically your problem solving, your critical thinking, they're your key skills. So don't be intimidated when you read a job ad and go, oh, it's in, I don't know, energy dispatch. I don't know anything about energy dispatch. And it says data analysis, you should be able to do this, this, and this. You can learn, right? You've got all the key skills and you just got to learn the domain. Learn to program. I know I've said the caveat that I've come from I like software developing a lot and I work as a software developer. You have to learn to program. Doesn't matter. Even if you like maths and stats, you have to learn to program it. There are two different types of programming. There's kind of like scripting and scientific programming, and there's like full-on software development, like writing programs for other people to use. They're slightly different. One is not necessarily better than the other, but they'll match different jobs. So an issue we get at Polymathian is that we hire software developers, and we often get very capable maths and stats background people who can program, but they don't know very many like software design principles or coding patterns. So it's just, I taught myself, you can learn. If you like it, you'll learn it, but they're different. You can pivot between the two. A really good, like Julia is a great language to learn. It's free. Python is probably the one, if you want to pivot towards software, Python is the one you're going to use most often. Particularly, I think that'll apply both to software as well as scientific programming. The thing, Julia's quite young. It doesn't have a lot of libraries yet, whereas Python has a library for everything. If you want to implement like the XYZ algorithm, someone's written a package for that and you can just use their code. So Python has the advantage of a huge code base. If you do want to pivot into software development, learn about object-oriented programming, learn about software design, learn about coding patterns. So won't go into this here. A good way to start can be to start at looking, so often in your assignments, you write your own code from scratch, learning to start from somebody else's code. and modify their code is really important. Learning to read and understand somebody else's code is really important. More for software than for scripting. Scripting, even so, like you could be a mathematician. So when I did this project, I developed all these asset models, right? Made 100, way too many R scripts, poorly named, 0001 all the way up to 11. And then I thought that was it. But then they came back a year later and they're like, can you refit our asset models? We've done some upgrades to the cogen. And I wasn't on this team anymore. I'd moved to a different team. So some poor person inherited all my scripts. How embarrassing. And they had to learn how to run them. So yeah, that's not very, learn how to read other people's code, because you could get absolute shit and you've got to learn how to read it and run it. Poor person who gets your code. So the one thing you can try is to make write your code as if someone is going to inherit it and has to run it. Or maybe you have to inherit it 2 years later. Someone goes, can you run that code again? You look at the script and you're like, I have no idea what I was thinking when I wrote this script. So try and think of that when you're programming. Learn version control. You have to learn version control. Doesn't matter whether you're doing programming or maths or stats, you have to learn version control. Every single job I've had in CSIRO, and this is CSIRO as a scientist, right? I wasn't a software developer, through to Polymathian where I'm a developer, has had version control. Version control on your own, like when you're the only person on the repository, it's very, very different to version control when other people are in the same code base. So at the moment, my team has about 10 to 15 people in it, and they're all touching the same code base every day. And so you've got to learn how to merge your, deal with merge conflicts, rebase your code on top of those. So it varies how much you have to learn with what you're doing. If you're a scientist kind of on your own, or not too many people are touching your code base, you can get away with less, but you still have to learn it. A good way to practice is on your assignments. It's not very useful on your assignments because generally you're just doing today's commit, tomorrow's commit. Yes, you're doing one commit per day rather than grouping them logically to question 1, question 2, tried question 2 again. Whoop, question 2, that didn't work. Let's go back to the previous version of question 2. But a good way to practice is on your own, like, for assignments where you don't have to deal with other people. And then I think this is the last thing. Sorry, this is really, really long talk. So you have to be ready to learn. So you're never going to know everything you need for a job when you go in. You're always going to learn it on the job. This is okay. Don't be intimidated by it. Your colleagues or the people who are hiring you know that you don't know much for the specific context. They're willing to train you or they would not have hired you. You have to bring your skills and then learn the domain and the context. Okay. And then the last, you can't ignore your soft skills. It's really sad. I know a lot of people don't like hearing this, but you can't ignore it. You can vary the dial a bit. In a bigger company, sometimes you can get a very targeted role that doesn't have a lot of client interaction. I purposely put myself on the other end where I do a lot of interaction, like I do a lot of different jobs, which necessitates a lot of interaction. So you can control that dial a bit, but you're always going to have to talk to someone. You might have to talk to your boss, who is a mathematician, but who has moved into management and so is a bit rusty on the details of the maths that you were doing. You're always going to have to talk to someone, and that person will almost certainly not know as much detail as you do about the specific thing that you are working on. So you can't get around this at all. Other tools, I'm going to leave this as a reference slide. There are lots of cool things. I don't know, do you use like Markdown or Jupyter in Julia? Oh, excellent. That was my main one. That's great for assignments. You don't need to write tech if you can use Markdown and embed just the mathsy bits of tech into the Markdown. Then you don't have to write the whole document in LaTeX, which is a nightmare. ggplot, if you're using R, Linux. This is the sad thing. Learn some Excel. Like if you're going to go into statistics, you have to learn some Excel. You might, like, you live in R land or Julia land and you're doing all this epic code, but at some point you're going to a client's going to email your spreadsheet, or you need to email a client back a spreadsheet, and it's going to be so much easier to do that in Excel rather than they can't edit your scripts because they don't know, right? Or sometimes even I've had to plot in Excel because they wanted to edit some of the plots, and you can't send them a script in R to do that if they're not an R person. Everyone speaks Excel, so learn some of that. Learn some Word, learn some PowerPoint. It's a bit sad, but do it. Final thoughts. Sorry, we're right on time. So don't be depressed. I know this is a little bit of like I don't know, stats is not as flash as you thought. You might think, oh, now I have to learn how to program and version control, and I have to learn how to talk to people. And I'm going to spend ages doing data mangling instead of doing fun stats. Don't be depressed. This is a perspective seminar. Maybe the other two will have different perspectives. I will be surprised if they do have radically different perspectives. But again, you can control the dial of all of these things. I deliberately seek out lots of variety and lots of interaction, and you can definitely control this. And then have fun. You can always change your job, right? If you don't like your job, just reskill. You're never locked in. That's everything. Thanks for listening. I don't know if we have time for questions because it's like 7 on the dot. You guys need to go. Go if you need to. I'll hang around if you want. Yep. Yeah, we use Plotly and Polymathian. It's it's not great for everything, but it's good for some things. It's like ggplot. Well, it's nowhere near as good as ggplot, but it's got really good front end support. So.
For making software like this, do you have to learn a lot of front end?
No, I didn't. So we're lucky. This framework is written in-house. It's called Tropify. So all of us plebs write Python. And we have a bunch of front-end people who map the Python into magic like this. I wouldn't be able to do any of that. Yep. We use Gurobi all the time. I've not used it at all before joining Polymathian. I had done 0 operations research before joining Polymathian, and I just learned it on the job. We use it all the time. So between Cblex and Gurobi, some of our problems, Gurobi is faster than Cblex, but Gurobi is much more expensive.
Any more questions?
Yep. If all the data, I've had a project where all the data is garbage, you just have to tell them all the data is garbage. Ideally, you don't accept money for a project in which all the data is garbage. You should do your due diligence and try and get them to send you a sample of the data beforehand. You might have to sign an NDA for it just to inspect it and convince yourself that it will not be garbage. I've had one project where it was all garbage. So it was a machine learning project. They said, oh, we've got thousands and thousands of data points. It's all labeled. Can you do this machine learning? Tell us basically when the ore is going to be contaminated or something. And we think we can tell from these sensors, rah, rah, rah. Great, send us all the data. They've got 4 data points. 4 data points. And each data point was each instance was several hours long of time series data. So they had thousands of individual rows, but only 4 distinct instances of the problem they were trying to detect. So yes, sometimes you just have to educate them. And then don't make that mistake again next time. When they say we have thousands of rows of labeled data, you need to get more detail from them. Lesson learned.
All right, if no one else has any questions for Amy, say thank you.
Thanks, guys.
Thank you very much.
Yeah. Just stop share. And right, see people. Cool.
Yep.